We have mapped galaxies billions of light years away, yet the universe is hiding its most fundamental secrets. By the end of this journey, you will see the frontiers of astrophysics through 30 mysteries that will reshape how you think about reality. Why does most of the universe's matter remain invisible? What force is tearing the cosmos apart at an accelerating rate? Our first stop is dark matter, the invisible scaffolding that holds galaxies together. What does it mean when the things we cannot see outnumber the things we can by a factor of 5? Galaxies spin so fast they should tear themselves apart. The stars and gas at the outer edges move at speeds that would send them flying away if only the visible matter were holding them together, and yet they stay. Something unseen, something massive, is gripping them with its gravity. That something is dark matter. It does not emit light, does not absorb it, does not reflect it. It is completely invisible to every telescope we have. The only way we know it exists is through its gravitational pull on the things we can see. Scientists measure the rotation curves of galaxies, plotting how fast stars orbit at different distances from the center. In a galaxy held together only by visible stars and gas, the outer stars should slow down, but they do not. They keep moving at nearly the same speed as stars closer in. For that to happen, there must be a vast halo of hidden mass surrounding each galaxy, a halo made of something we have not yet identified. Another piece of evidence comes from gravitational lensing. When light from distant galaxies passes through the gravity of a massive cluster, the path bends, creating distorted arcs and rings. By analyzing those distortions, astronomers can calculate the total mass of the cluster. And that mass is far larger than what the stars and gas add up to. The difference, dark matter again. Pulling all these observations together, we find a stunning ratio. For every 1 kilogram of ordinary matter, there are about 5 kilograms of dark matter. The stuff we are made of, the stars, the planets, the dust, everything we can touch and see, accounts for less than a fifth of all the matter in the universe. The rest is a ghost that passes through us and through the Earth without leaving a trace. So what is it made of? The leading candidates are particles that interact so weakly with normal matter that they almost never bump into it. Theorists have proposed weakly interacting massive particles, or WIMP, which would be heavy and slow-moving, and actions, which would be extremely light and abundant. For decades, physicists have built experiments deep underground, shielded from cosmic rays, hoping to catch a rare collision between a dark matter particle and an atomic nucleus. They have set up tanks of liquid xenon, crystals of germanium, and chambers of superheated liquid. They have watched and waited for years. So far, nothing. The detectors have seen only silence and background noise. That null result is itself a clue. It tells us that dark matter interacts even more weakly than many hoped, or that its mass falls outside the range we have been searching. The search is not over. It is pushing us to build bigger and more sensitive experiments. Meanwhile, the James Webb Space Telescope is offering a new angle. By peering back to the earliest galaxies, Webb can see how structure formed when the universe was only a few 100 million years old. Those early galaxies appear to have grown faster than our models predicted, suggesting that dark matter might behave differently than we assumed. Webb is giving us a front-row seat to the cosmic scaffolding, and the more we look, the more we realize how much we do not know. The invisible mass that dominates the universe remains stubbornly hidden, and every failed detection only deepens the mystery. What kind of particle can account for 5 times the mass of everything we see and still refuse to show itself? That question drives one of the most urgent searches in all of science. And it is only the beginning of our journey into the unknown. The universe is not just expanding, it is speeding up. In the late 1990s, 2 teams of astronomers were studying distant supernova to measure how fast the cosmos was slowing down. They expected that gravity from all the matter in the universe would gradually break the expansion, like a ball rolling uphill and losing speed, but what they found turned everything on its head. The supernova were dimmer than predicted, meaning they were farther away than expected. The expansion was not slowing, it was accelerating. Something was pushing the universe outward, a kind of anti-gravity that we now call dark energy. This entity is not something we can see or touch, but its fingerprint is written across the largest scales. In fact, dark energy accounts for about 68% of the total energy density of the universe. Combined with dark matter, that leaves ordinary matter as just a tiny sliver, less than 5%. The accelerating expansion shows that dark energy is not just a small correction. It is the dominant force shaping our cosmic future, yet its origin is a complete blank. The leading idea comes from quantum field theory, the branch of physics that describes the behavior of particles and fields at the smallest scales. According to that theory, even empty space is not truly empty. It is filled with tiny, fleeting energy fluctuations. Those fluctuations should act like a kind of background pressure, and mathematically they behave exactly like a cosmological constant, a term that Albert Einstein once added to his equations, then later called his biggest mistake. But when physicists calculate the size of that vacuum energy, they get a number that is staggeringly large, about 10 to the 120 times bigger than what we actually observe. That mismatch is known as the cosmological constant problem, and it is arguably the most embarrassing discrepancy in all of science. Either our understanding of quantum fields is missing something fundamental, or dark energy is something else entirely, perhaps a new field that changes over time. Imagine trying to predict your electricity bill and being off by a factor of 1 trillion. That is the kind of gap we are dealing with. So dark energy remains a profound mystery. It controls the fate of the cosmos, pushing galaxies apart faster and faster, yet we have no direct evidence of what it is. Every new survey of supernova, every measurement of the cosmic microwave background, and every study of how galaxies cluster together adds another piece to the puzzle. But so far the pieces do not form a clear picture. The universe is running away from us and we cannot explain why. That unanswered question points to the next frontier, a place where the very structure of spacetime itself may hold the key. The most extreme objects in the universe are also the most secretive. Black holes are regions where gravity has become so intense that nothing, not even light, can escape. We have now imaged the shadow of a supermassive black hole in the galaxy Messier 87, and we have detected the ripples in spacetime from merging black holes using observatories like LIGO and Virgo. But those observations only reveal the outskirts, the event horizon, the point of no return. Once something crosses that boundary, all information about its structure, its composition, its very identity is lost to the outside universe. Inside, our familiar laws of physics break down completely. According to classical general relativity, all the matter that falls into a black hole ends up crushed into an infinitely dense point called a singularity. At that point, density becomes infinite, gravity becomes infinite, and the equations that describe the warping of spacetime simply stop working. A singularity is a mathematical signal that the theory has reached its limit. It tells us that we need a deeper understanding, and that deeper understanding must come from quantum gravity, a framework that merges Einstein's relativity with the strange rules of quantum mechanics. We do not yet have a complete theory of quantum gravity, but we have hints about what might replace the singularity. Some models suggest that instead of a point, the interior contains a tiny, highly curved region where spacetime itself is foamy and fluctuating. Others propose that the black hole interior is not a one-way trip, but a bridge to another part of the universe, what we call a wormhole. These ideas are speculative, but they point to a profound truth. The black hole interior is the ultimate test of our understanding of reality. The tension between general relativity and quantum mechanics becomes most visible in two famous paradoxes. The first is the firewall paradox. It asks what happens when you try to combine the smooth, continuous picture of spacetime with the quantum mechanical rule that information cannot be destroyed. If a black hole slowly evaporates by emitting Hawking radiation, then the radiation carries away energy, but does it carry information? If not, information is lost, violating quantum mechanics. But if it does, then the radiation must be entangled with something that fell in, leading to a violent burst of energy at the event horizon, a firewall that would incinerate anything crossing it. This would contradict general relativity, which says that crossing the horizon should feel like passing through an ordinary patch of space. So either our understanding of quantum mechanics is wrong, or our understanding of gravity is wrong. The second is the information paradox itself. Stephen Hawking originally argued that information swallowed by a black hole is permanently lost, but later work, especially by Leonard Susskind and Gerard T. Hooft, suggested that information might be stored on the event horizon itself like a hologram. This idea, known as the holographic principle, proposes that the three-dimensional interior of a black hole is actually encoded on its two-dimensional surface. If that is true, then the universe itself might be a kind of hologram, with all the information about the cosmos stored on a distant boundary. String theory, one of the leading candidates for a theory of quantum gravity, provides a concrete framework for this holographic correspondence. In string theory, black holes can be described as collections of tiny vibrating strings, and their entropy, the measure of their hidden information, matches perfectly with the area of the event horizon. This is one of the few successes we have in connecting gravity to quantum mechanics, yet it remains a mathematical duality, not a full physical picture. We still do not know what actually happens inside a black hole. The singularity may be replaced by a new state of matter, or the interior may simply not exist in the way we imagine. Each new observation of gravitational waves from merging black holes gives us a chance to test these ideas. The signals we see match the predictions of general relativity extremely well, but they only tell us about the outside. The interior remains the last great unknown in the heart of darkness. And as we push deeper into that mystery, we are forced to confront the most fundamental question of all: what is space-time made of? Out in the dark between galaxies, something is sending us short, powerful messages. They last only a few thousandths of a second, yet in that fleeting moment they release more energy than the sun does in an entire year. These are fast radio bursts, and since their discovery in 2007, they have become one of the most puzzling signals in astrophysics. A fast radio burst, or FRB, is a millisecond-long flash of radio waves that arrives from somewhere far beyond our own galaxy. Most of them burst only once, a single scream from the cosmos that never repeats, but a small fraction, fewer than 50 so far, have been seen to repeat, sometimes hundreds of times from the same location. That distinction is a crucial clue. It tells us that whatever causes these events can either destroy itself in the act or survive to burst again. The leading explanation points to magnetars, the most magnetic objects known. A magnetar is a type of neutron star, the crushed core of a massive star that exploded as a supernova. Its magnetic field is a billion times stronger than Earth's, so intense that it can warp the atoms around it. When that field suddenly reconfigures like a rubber band snapping, it can release an enormous blast of energy. That energy, traveling across the universe, arrives at our telescopes as a fast radio burst. The case for magnetars grew stronger in 2020 when a known magnetar in our own galaxy, SGR 1935+21, emitted a burst of radio waves that looked exactly like a faint FRB. It was the first time scientists had seen an FRB equivalent from inside the Milky Way, linking a specific object to the phenomenon, but that single event also raised new questions. The energy of that local burst was far weaker than the FRBs we see from other galaxies. To match the power of the brightest extragalactic bursts, a magnetar would need to release something like 1,000 times more energy than it did here at home. That is not impossible, but it pushes our models to their limit, and the mystery deepens when we look at where the repeating FRBs come from. Some repeaters are found in dwarf galaxies that are forming new stars at a furious rate, environments rich in young magnetars. Others come from massive elliptical galaxies that are old and quiet, places where magnetars should be extremely rare. A few have even been traced to the edges of their host galaxies, far from the regions where neutron stars are normally born. Each new localization seems to tell a different story, as though FRBs can arise from multiple pathways. Perhaps some come from magnetars, others from the collision of neutron stars, and still others from something we have not even imagined. What makes FRBs so valuable is not just the mystery of their origin, but the fact that they travel across the universe, passing through the thin gas that fills the space between galaxies. That gas leaves a fingerprint on the radio waves. When the burst travels through the intergalactic medium, the plasma slows down the lower frequency waves more than the higher ones, creating a delay known as dispersion. By measuring that delay, astronomers can calculate how much matter the signal passed through. In effect, each FRB acts like a probe, allowing us to weigh the invisible gas that lies between galaxies, gas that is otherwise almost impossible to detect. This technique has already provided some of the best measurements of the density of matter in the intergalactic medium, confirming that ordinary baryonic matter is there, hiding in wispy filaments that stretch across cosmic voids. The more FRBs we detect, the more we can map the large-scale structure of the universe, filling in the missing pieces of cosmic web. Yet for all that power, the fundamental question remains unanswered. What exactly makes these bursts? We have a leading candidate in magnetars, but the range of energies, the variety of host galaxies, and the existence of both repeating and one-off events suggest that nature may have more than one way to create a fast radio burst. A unified model still eludes us. Every new detection adds a data point, narrowing the possibilities, but we are not there yet. And as the instruments grow more sensitive, the number of known FRBs is climbing exponentially. With thousands expected in the next few years, the mystery is only going to deepen. Each burst is a messenger from a place we cannot see, carrying the signature of an extreme event that we are only beginning to understand. Rewind the clock to the very first fraction of a second after the Big Bang. The universe was not just expanding, it was stretching at a rate beyond anything we see today. In less time than it takes light to cross a single proton, the cosmos doubled in size again and again, ballooning from a quantum speck to something billions of times larger. This brief, explosive burst is called cosmic inflation, and it reshapes everything we thought we knew about the origin of everything. The theory of inflation proposes that for an incredibly short interval, the universe underwent exponential expansion, driven by a strange energy field that repelled instead of attracted. That field, often called the inflaton, infused empty space with a powerful repulsive force, causing spacetime itself to blow up like a bubble. When inflation ended, the energy of that field decayed into a hot, dense soup of particles and radiation, setting the stage for the familiar Big Bang expansion we observe today. Why do cosmologists believe in this fleeting moment? Two classic puzzles point to it. The first is the horizon problem. When we look at opposite sides of the sky, the cosmic microwave background radiation is nearly identical in temperature. But those two patches are so far apart that, in a standard Big Bang model without inflation, no signal could have traveled between them to even out the temperature. They would have been out of causal contact since the beginning, yet they are almost exactly the same. Inflation solves this by saying that those separated patches were once microscopically close together before the rapid expansion pushed them apart. They had time to reach the same temperature before being ripped away. The second puzzle is the flatness problem. We measure our universe to be geometrically flat, meaning that parallel lines never meet and the total energy density is right at a critical value. In standard Big Bang theory, any tiny deviation from flatness would have grown over time. To stay as flat as we see today, the universe would have had to be tuned to an absurdly precise degree at the beginning, something like 1 part in 10 to the 60. That seemed like a bizarre fine-tuning. Inflation solves it by stretching any initial curvature out so much that it becomes indistinguishable from flat, like blowing up a crumpled balloon until it is smooth. Inflation also provides a natural explanation for the seeds of all cosmic structure. Quantum fluctuations during the rapid expansion were stretched to astronomical scales, creating tiny variations in density. Those variations later grew into galaxies and clusters. The pattern of these fluctuations matches what we observe in the cosmic microwave background with astonishing accuracy. It is one of the greatest successes of modern cosmology, yet for all its explanatory power, inflation remains unproven. The simplest models of inflation predict a specific signature, primordial gravitational waves. These ripples in spacetime, generated during the exponential expansion, would leave a faint imprint on the polarization of the cosmic microwave background, a pattern called B-mode polarization. Detecting that pattern would be a direct confirmation that inflation happened and would give us a glimpse of the energy scale at work. For years, experiments like BICEP and Keck have been scanning the sky from the South Pole, searching for that elusive signal. In 2014, the BICEP-2 team announced they had found B-mode polarization, but it turned out to be from galactic dust, not primordial waves. Since then, the search has continued with ever more sensitive instruments. The Simons Observatory and the next-generation SIMBI experiments are pushing the limits, hoping to catch the faint whisper of gravity from the first moments. So far, nothing. The absence of a detection is tightening constraints on which models of inflation could be correct, but it has not ruled out the basic idea. Meanwhile, alternative theories still exist. Bouncing cosmologies suggest that our universe did not begin from a singularity, but instead contracted to a very dense state and then bounced outward. These models can also solve the horizon and flatness problems without inflation, though they come with their own challenges. The debate is active and healthy. Inflation is the leading idea, but it is not the only game in town. What makes this search so compelling is that we are probing the very first moments of existence, a time when energies were so high that our understanding of physics breaks down. If we ever detect those primordial gravitational waves, we will have a direct window into a regime that physics has never accessed before. And if we do not, we will have to rethink some of our most cherished assumptions. Either way, the answer is out there, encoded in the faint glow left over from the dawn of time. Two different ways of measuring the expansion rate of the universe give two different answers. Astronomers call this the Hubble tension, and it is not a minor disagreement. It is a stubborn, growing chasm between the value we get by looking at the local universe and the value we get by studying the cosmic microwave background, the leftover glow from the Big Bang. The local method uses distance ladders. It starts with Cepheid variable stars which pulsate at a rate tied to their true brightness. By comparing that true brightness to how dim they appear from Earth, we calculate their distance. Then we layer on Type 1, a supernova which explode with a consistent peak luminosity. These supernova act as cosmic lighthouses, visible across billions of light years. By combining Cepheids and supernova, we trace the expansion rate out to hundreds of millions of light years. That measurement yields a Hubble constant of about 73 kilometers per second per megaparsec. A megaparsec is 3.26 million light years, so for every megaparsec farther away a galaxy is, it appears to recede 73 kilometers per second faster. Now compare that to the early universe measurement. The cosmic microwave background provides a snapshot of the universe when it was only 380,000 years old. From that snapshot, we can calculate what the expansion rate should be today, assuming our standard model of cosmology, which includes dark matter and dark energy. That prediction gives a significantly lower value, around 67 kilometers per second per megaparsec. The difference is about 6%. 6% might sound small, but the uncertainties on both measurements have been shrinking for decades. As the error bars tighten, the discrepancy does not go away. It actually grows more statistically significant. Today, the tension stands at 5 sigma. In physics, 5 sigma is the gold standard for a discovery. It means the odds that the two values agree by random chance are less than 1 in 3.5 million. That is not a measurement error. That is a signal that something fundamental is missing from our models. So what could explain it? One possibility is early dark energy, a hypothetical form of energy that briefly dominated the early universe and then decayed away. If early dark energy existed, it would have changed how fast the universe expanded after the Big Bang, which in turn would alter the imprint we see in the cosmic microwave background. By adding a dash of early dark energy, the predicted value from the early universe can be nudged upward closer to the local measurement. Another possibility is modified gravity. Perhaps on very large scales, gravity behaves slightly differently than Einstein's theory predicts. If gravity were a little bit stronger in the early universe, it would have slowed expansion then, changing the CMB prediction. A third idea involves exotic dark matter, a form that interacts with itself or with other particles in ways we have not yet anticipated. Self-interacting dark matter could alter the formation of cosmic structures and shift the inferred expansion rate. Each of these ideas has its own strengths and weaknesses. Early dark energy is elegant but requires a fine-tuned onset and decay. Modified gravity runs into constraints from other observations. Exotic dark matter lacks direct experimental support. All of them are, at this stage, conjectures. But the fact that the tension has reached 5 sigma means we can no longer comfortably ignore it. The standard model of cosmology, known as lambda CDM, has been remarkably successful. It explains the cosmic microwave background, the distribution of galaxies, and the abundance of light elements. But the Hubble tension is a crack in the facade. It suggests that something new lies beyond the model, a particle, a field, or a modification of spacetime that we have not yet identified. This is what makes the Hubble tension so exciting. It is not a failure of our instruments, it is a clue. Every new observation from the James Webb Space Telescope, the Dark Energy Spectroscopic Instrument, and the upcoming Nancy Grace Roman Space Telescope will sharpen the measurements further. If the tension persists and grows, it will force a revision of the standard model. If it resolves, it will test our understanding of systematic errors in the distance ladder. Either way, we are learning something profound. The universe is giving us a direct hint that our current picture of its expansion is incomplete, and that hint is one of the hottest topics in cosmology today. For every particle of matter in the universe, there should be a matching particle of antimatter, but there is not. When matter and antimatter meet, they annihilate each other in a flash of pure energy. If the Big Bang had created equal quantities as our most fundamental theories predict, then just moments after the birth of the cosmos, all the matter and antimatter would have wiped each other out, leaving behind nothing but radiation and a few leftover scraps. Yet here we are, made of matter, on a planet of matter, in a universe dominated by matter. Somewhere in the earliest instance, a tiny imbalance was built in, an asymmetry on the order of 1 part in a billion. For every billion antimatter particles, there were a billion plus 1 matter particles. That minuscule surplus after the Great Annihilation is what now fills the galaxies, the stars, the planets, and us. The question is, how did that asymmetry arise? In the 1960s, the Soviet physicist Andrei Sakharov laid down 3 conditions necessary for the universe to develop a matter-antimatter imbalance. First, there must be processes that violate baryon number, the quantum number that counts particles like protons and neutrons. In the standard model of particle physics, baryon number is almost always conserved, but certain high-energy interactions, still theoretical, could break that rule. Second, there must be a violation of C-symmetry, which flips particles to antiparticles, and CP symmetry, which in addition flips the spatial coordinates. CP violation is a known effect. It was discovered in the 1960s in the decays of kaons and later confirmed in B mesons. But the amount of CP violation we see in the standard model is far too small to account for the observed asymmetry. The third condition is a departure from thermal equilibrium. If everything were perfectly balanced and in thermal equilibrium, any asymmetry created would be erased by reverse reactions. The universe must have been changing fast enough, for example during a phase transition or the decay of a heavy particle, to lock in the imbalance. These 3 Sakharov conditions are the framework, but they do not tell us exactly how nature achieved the imbalance. The 2 leading hypotheses are electroweak baryogenesis and leptogenesis. Electroweak baryogenesis proposes that the asymmetry was generated during the electroweak phase transition, a moment early in the universe when the electromagnetic and weak nuclear forces separated. This transition, if it were strong enough and first order, could have created the out-of-equilibrium conditions needed. At the same time, the interactions involving the Higgs field would have provided the necessary CP violation. The problem is that the standard model Higgs mechanism does not offer enough CP violation, and the electroweak phase transition in the standard model would not have been strong enough. Extensions of the standard model, like adding extra Higgs particles or new sources of CP violation, might save the idea, but so far no experimental evidence supports them. The second hypothesis, leptogenesis, takes a different route. It suggests that the asymmetry first appeared in the lepton sector, the family of particles that includes electrons, muons, and neutrinos. In this scenario, heavy right-handed neutrinos, particles not present in the standard model, would have decayed in the early universe in a way that violated lepton number and CP symmetry. Those decays created an excess of leptons over antileptons. Then, through processes called sphalerons, which are known to be active at high temperatures, that lepton asymmetry was converted into a baryon asymmetry. Leptogenesis is attractive because the existence of heavy right-handed neutrinos also naturally explains why the known neutrinos have such tiny masses, a phenomenon called the seesaw mechanism. Yet even leptogenesis remains unconfirmed. The heavy neutrinos have never been directly detected, and their masses are far beyond the reach of current particle accelerators. So how are we searching for the missing piece? Experiments like LHCb, one of the detectors at the Large Hadron Collider, are hunting for CP violation in processes that go beyond the standard model. By measuring the decays of beauty hadrons and charm hadrons with extreme precision, LHCb can look for subtle differences between matter and antimatter behavior that do not fit the standard model predictions. If any such deviation appears, it would be a direct sign of new physics that could drive baryogenesis. Another avenue is the search for neutron-antineutron oscillations. If baryon number violation occurs, a neutron could spontaneously transform into an antineutron, a process that flips its quantum number. Experiments like the ones at the European Spallation Source are trying to detect this oscillation. Observing it would prove that baryon number is not sacred, fulfilling the first Sakharov condition. So far, all searches have come up empty. The standard model holds firm, and the origin of matter remains elusive. But the very fact that we exist tells us that the asymmetry is real. Some unknown mechanism operating in the first fractions of a second after the Big Bang tipped the balance in favor of matter. Every new search, every higher precision measurement narrows down the possibilities. And when that mechanism is finally identified, it will not only explain why we are here, it will reveal a new layer of fundamental physics that governs the universe at energies we can barely imagine. A single cosmic ray can carry the energy of a well-thrown baseball. That is not an exaggeration. Some particles arriving from deep space pack more punch than anything our most powerful particle accelerators can produce by a factor of millions. These are ultra-high energy cosmic rays, and their existence is one of the most stubborn puzzles in astrophysics. We know what they are, mostly protons and atomic nuclei, accelerated to speeds incredibly close to light. But we do not know where they come from. The sources must be extreme, objects capable of accelerating particles far beyond the reach of supernova shockwaves or stellar flares. The leading suspects are active galactic nuclei, the supermassive black holes at the centers of galaxies that blast out jets of matter and energy. Gamma-ray bursts, the most luminous explosions in the universe, are another candidate. So are the violent collisions of neutron stars. Yet when we look at the sky in the directions from which these cosmic rays arrive, we do not see a clear source. There is no obvious active galaxy or bright explosion pointing back at us. The particles themselves give few clues. They are electrically charged, so as they travel across the universe, magnetic fields bend their paths. By the time they reach Earth, their original direction is scrambled, making it nearly impossible to trace them back to their birthplace. Only the highest energy particles, those with the least amount of bending, offer a chance at pinpointing a source. And that is where the mystery deepens. The energy spectrum of cosmic rays is not a smooth curve. It shows a feature astronomers call the knee. At around 1,000 trillion electron volts, the number of particles arriving begins to drop off more steeply. The knee tells us that there is a change in how these particles are accelerated or how they travel through the galaxy. It might mark the limit of what supernova remnants can produce. Below the knee, cosmic rays likely originate within our own Milky Way. Above it, the particles become rarer and are almost certainly extragalactic. And then, at the very highest energies, around 50 trillion electron volts, there is a cutoff. That cutoff is not a mystery in itself. It is the result of a prediction made by Kenneth Greisen, George A. Zatsepin, and Vadim Kuzmin, now known as the GZK limit. A particle with that much energy cannot travel very far through the universe. On its journey, it will eventually collide with photons of the cosmic microwave background, the faint afterglow of the Big Bang. Those collisions produce new particles and drain energy from the original proton. So any cosmic ray we detect above that cutoff must have come from relatively nearby sources within 100 million light-years or so. That is a small distance on cosmic scales, but within that volume we still see no obvious source. The galaxies are quiet, the active nuclei are rare. Either that nearby region contains a hidden accelerator, or our understanding of the particle interactions is incomplete. To study these elusive visitors, the Pierre Auger Observatory was built. It covers an area of 3,000 square kilometers in the plains of western Argentina, a patch of land larger than the country of Luxembourg. The observatory uses two methods simultaneously. An array of 1,600 surface detectors, each a tank of purified water, sits spaced 1.5 kilometers apart. When a cosmic ray strikes the atmosphere, it creates a cascade of secondary particles, a shower that rains down over many square kilometers. Those particles hit the water tanks and produce tiny flashes of light recorded by sensors. At the same time, fluorescence detectors placed on high ground around the array watch the night sky for the faint ultraviolet glow that the shower leaves as it tears through the air. By combining both signals, scientists can reconstruct the energy and direction of the original cosmic ray with remarkable precision. The observatory has detected thousands of events at the highest energies. It has confirmed the GZK cutoff, showing that the flux of particles drops sharply as predicted. but it has also found a handful of events that seem to come from directions with no obvious source. A few of these point toward nearby active galaxies, but the statistics are weak. There is no overwhelming signal. The search for the origin of ultra-high energy cosmic rays is one of the great unfinished stories in astrophysics. Every new event, every new shower recorded by the Pierre Auger Observatory adds a data point to a sparse map. With time, we may begin to see a pattern, a clustering of directions that reveals the source population. Or we may find that the sources are so rare and so weak that we need an even larger observatory, perhaps one that covers 100,000 square kilometers to see them clearly. Until then, the most energetic particles in the universe continue to arrive from the void, messengers without a return address, and each one carries a clue about the most violent and powerful places in the cosmos, places we can barely imagine. Our Milky Way is being pulled sideways through the universe at 2 million kilometers per hour. That is not an orbit around anything local. It is a steady drift, a coherent flow that involves our galaxy and hundreds of its neighbors, all sliding together toward a single point in the constellation Norma. Astronomers call that point the Great Attractor, and for decades it has been one of the most frustrating hidden objects in the sky. The problem is that the Great Attractor lies behind the plane of our own galaxy, the thick band of dust and gas that blocks visible light. We cannot see it with ordinary telescopes. The dust is so dense that it absorbs almost all optical light from beyond. It is like trying to read a street sign through a blizzard. So to study this mysterious pull, astronomers have turned to radio waves and X-rays which can cut through the dust. Radio observations reveal a huge concentration of mass there, a dense cluster of galaxies known as the Norma cluster, and a supercluster of thousands of galaxies beyond it. But the total mass we see in those galaxies is not enough to account for the huge velocity of the local group. Something else, some hidden overdensity, must be adding extra gravitational pull. The Great Attractor itself may be part of a much larger structure, the Shapley supercluster, which sits about 650 million light-years away and contains the mass of 10,000 Milky Way galaxies. The Shapley supercluster is the most massive concentration of galaxies within 1 billion light-years of us. Its gravity may be the dominant influence on the large-scale flow of galaxies across the local universe. But whether the Shapley supercluster fully explains the motion is still debated. Some studies suggest that there is an even more distant pull, perhaps from the dipole repeller, a region of unusually low density that pushes galaxies away from it, adding to the apparent attraction. The data from surveys like the Hubble Space Telescope's Cosmic Flows project and the radio surveys of neutral hydrogen are mapping the velocities of thousands of galaxies. Those velocities trace the gravitational landscape, and what they show is a web of flows converging toward several nodes, with the Great Attractor region as one of the strongest. Yet the exact source remains invisible. We have measured its pull with increasing precision, but we have not directly imaged its heart. The mystery is not whether the Great Attractor exists, but what it ultimately contains. Could it be a collection of clusters so rich that they are hidden from our view by the galactic plane? Could there be additional dark matter clumps that we have not yet accounted for? Or is the entire local universe being funneled toward a much larger basin of attraction, one that extends far beyond what we can currently map? Each new survey, each new measurement of peculiar velocities adds another brushstroke to this hidden portrait, but the blizzard of dust still hides the central figure. The Great Attractor remains a gravitational ghost, a force we feel but cannot fully see, and the story of our own galaxy's motion through the cosmos is still being written. Perhaps the motion is not caused by hidden mass at all. What if the law of gravity itself is different on the largest scales? That idea, known as modified Newtonian dynamics or MOND, was first proposed in the 1980s by the physicist Mordechai Milgram. He noticed something striking: the rotation curves of galaxies, the very same evidence that led to dark matter, could be explained without any invisible substance if gravity behaved differently at very low accelerations. In everyday life, Newton's law of universal gravitation works perfectly. Drop an apple and it falls. Send a satellite into orbit and its path follows Newton's equations to many decimal places. But Milgram suggested that when gravitational acceleration drops below a certain tiny threshold, roughly a 10/1000th of what we feel on Earth's surface, gravity becomes stronger than Newton predicts. This modification removes the need for dark matter halos in galaxies. The math works out beautifully for spiral galaxies. If you apply MOND to the rotation curve of a typical galaxy, the predicted rotation speeds match the observed data with almost no free parameters. The fit is often as good as or better than a dark matter model that has to be tweaked for each galaxy. That is a powerful achievement, but MOND runs into trouble when we move beyond individual galaxies. For galaxy clusters, the modification is not enough. Clusters like the Coma cluster still require some invisible mass to hold them together, even with MOND. That extra mass could be ordinary matter in the form of neutrinos or diffuse gas, but the required amount is far more than what is observed. And then there is the cosmic microwave background. The pattern of temperature fluctuations we see across the sky is exquisitely explained by the standard model with dark matter. MOND has no natural way to produce those ripples because it does not change the physics of the early universe in the right way. So we are left with a dilemma. Either the universe is filled with an exotic new particle that we have never detected, or our theory of gravity is incomplete. Both options require new physics. Neither has been confirmed. In recent years, the debate has sharpened with new observational tests. Dwarf galaxies, small and faint systems that orbit larger galaxies like the Milky Way, provide a crucial laboratory. In dwarf galaxies, the gravitational acceleration is so low that MOND should show its effect most clearly. And indeed, many dwarf galaxies follow a tight relationship called the baryonic-Tully-Fisher relation, a correlation between their visible mass and rotation speed that matches the MOND prediction. But some dwarf galaxies, particularly the ultra-faint ones, show behavior that does not fit easily. Their velocities are too low, or their dark matter profiles are too cored, meaning less dense in the center than MOND would predict. Another test comes from wide binary stars, pairs of stars that orbit each other at vast distances, tens of thousands of astronomical units apart. At those separations, the gravitational acceleration is extremely weak. If MOND is correct, the orbits of these binaries should deviate from Newtonian predictions by a small but measurable amount. Astronomers are now using telescopes like Gaia to measure the motions of thousands of wide binaries with exquisite precision. The results so far are mixed. Some studies claim to see an anomaly consistent with MOND, while others find only Newtonian behavior within the uncertainties. The jury is still out. The challenge is profound. We have two competing ideas that both explain part of the data, but neither can account for everything. Dark matter fits the cosmic microwave background and galaxy clusters, but requires a particle we cannot find. MOND fits galaxy rotation curves beautifully, but fails on larger scales and in the early universe. Perhaps the truth is a synthesis, a modified theory of gravity that also includes a new particle, or a new form of dark matter that behaves differently in low acceleration environments. Or perhaps both ideas are wrong and a completely unexpected solution awaits. Every new measurement of a rotation curve, every study of a dwarf galaxy, every precise tracking of a wide binary star is a step toward breaking the deadlock. The universe is whispering that our understanding of gravity may not be the full story, and that whisper is growing louder. Our own solar system still holds secrets we cannot explain. Beyond the orbit of Neptune, the known planets give way to a vast, dim region of icy debris called the Kuiper Belt. Thousands of objects have been catalogued there, from small rocky fragments to dwarf planets like Pluto and Eris. But the Kuiper belt is not the edge. Far beyond it, stretching perhaps halfway to the nearest star, lies a hypothetical shell of comets known as the Oort cloud. The Oort cloud has never been directly observed. It is inferred entirely from the orbits of long-period comets. Those comets come from such great distances that their paths take tens of thousands of years to loop around the Sun and retreat. To reach us, they must originate from a vast reservoir of icy bodies, a sphere that surrounds the entire solar system, but we cannot see that reservoir. We only know it must be there because of the comets that randomly fall inward, nudged by the gravity of passing stars or by the galactic tides. The structure of the Oort cloud, its mass, its inner boundary, its total number of objects, all of these are educated guesses. We do not have direct images. We do not have probes traveling there. The outer solar system remains a frontier of inference rather than observation. And within that frontier, something strange is happening. In the late 20th century, astronomers began finding a new class of objects in the outer Kuiper belt, extreme trans-Neptunian objects with orbits that are highly elongated and steeply inclined. As more of these objects were discovered, a pattern emerged. Their orbits are clustered in a very particular way. They all seem to align in the same direction, as if something massive and unseen is herding them. That something is the hypothetical planet 9. The clustering is not random. Statistical analysis shows that the odds of such an alignment occurring by chance are extremely low, less than 1%. The best explanation is that a planet with a mass of about 5 to 10 times that of Earth, orbiting hundreds of times farther from the Sun than our planet does, is sculpting the orbits of these distant rocks with its gravity. This planet would be a dark, cold world, taking 10,000 to 20,000 years to complete a single orbit. It would be so faint that no telescope has yet spotted it. And its existence would explain not just the clustering of the extreme objects, but also the tilt of the entire solar system's plane relative to the Sun's equator, and the presence of certain objects that come from a strange, perpendicular direction. The search for Planet 9 is one of the most exciting observational hunts in modern astronomy. Telescopes like the Subaru telescope in Hawaii and the Dark Energy camera in Chile are scanning the sky, looking for a faint moving dot against the backdrop of billions of stars. The search area is enormous, hundreds of thousands of square degrees. The planet could be anywhere along a vast orbital path. It could be so dim that it is near the limit of detection, requiring careful subtraction of background light and repeated imaging over many nights. So far, nothing definitive has been found, but the evidence keeps piling up. In 2021, a study of distant Kuiper belt objects found that their orbits are not just clustered, they are tilted in a way that strongly supports the Planet 9 hypothesis. Another study in 2023 identified a new set of extremely distant objects that follow the same pattern. The planet is not a sure thing, but it is the most promising lead. If it exists, it would be the first new planet discovered in the solar system since Pluto was downgraded, and it would change our understanding of how our planetary system formed. Some simulations suggest that Planet 9 might be a rogue planet captured from another star system, or a core that was ejected from the inner solar system early in its history. Either way, its discovery would rewrite textbooks, but the hunt is challenging. The planet is likely 1,000 times fainter than the faintest star we can see with the naked eye. It is farther from the Sun than Neptune by a factor of 10 or more, and it moves so slowly that spotting its motion requires years of careful observation. Yet the search continues, driven by the conviction that something is pulling those distant objects in ways that our current catalogue of planets cannot explain. The outer solar system is not empty. It is a puzzle waiting for a key, and every new discovery of an extreme trans-Neptunian object brings us a step closer to finding that key, or to realizing that the puzzle is more complex than we ever imagined. Deep inside a collapsing star, the physics is still a mystery. We know the broad strokes of how a massive star ends its life. After millions of years of fusion, its core runs out of fuel, and the inward crush of gravity suddenly overwhelms the outward push of thermal pressure. The core collapses at nearly a quarter of the speed of light, crushing itself into a ball of nuclear matter no larger than a city. Then a rebound happens. The inner core bounces, sending a shockwave outward that should, in theory, tear the star apart. But that shockwave stalls. It loses energy as it plows through the outer layers, and within milliseconds it fizzles out. Something else must revive it, something that turns a dying whimper into a cataclysmic explosion. That something is neutrinos. During the collapse, the core becomes so dense and hot that it begins to emit an enormous number of neutrinos, ghostly particles that barely interact with matter. In a normal environment, neutrinos pass straight through everything, but in the collapsing core, the density is so extreme that even neutrinos get trapped. They stream outward from the very center, carrying away vast amounts of energy. As they pass through the stalled shockwave, a tiny fraction of them, less than 1%, deposit their energy into the surrounding gas. That energy reheats the shock, pushing it outward again. This is the neutrino heating mechanism, and it is the leading candidate for how supernova actually explode. But the details are fiendishly complex. The heating process is not steady. It is chaotic. The stalled shockwave is not a smooth spherical shell. It wobbles and sloshes, driven by instabilities that grow from tiny perturbations. The most important of these is the standing accretion shock instability, or SASI. This instability causes the shock to oscillate and slosh back and forth, like a balloon being squeezed unevenly. Those sloshing motions allow the neutrinos to heat certain pockets of gas more efficiently, creating bubbles of hot material that rise like plumes in a boiling pot. Those rising bubbles then collide with the shock, injecting extra energy at just the right spots. In the best simulations, this combination of neutrino heating and SASI is enough to trigger an explosion. But it is a delicate balance. Change the mass of the star by a few percent, or tweak the rate of neutrino emission, and the explosion may fail. The core collapses into a black hole with no supernova at all. And then there is the role of rotation and magnetic fields. In some massive stars, the core spins rapidly. As it collapses, that rotation speeds up, just like an ice skater pulling in their arms. The spinning core can become a dynamo, generating magnetic fields trillions of times stronger than Earth's. Those magnetized fields can channel energy into narrow jets, drilling a path through the star and triggering a different kind of explosion, a magnetorotational supernova. These are rare but real. They produce some of the most extreme events we see, like hypernova and long gamma-ray bursts, but how often they happen and under what conditions remains unclear. For decades, astrophysicists have been running ever more sophisticated simulations on the world's fastest supercomputers. The earliest models were one-dimensional, treating the star as a simple sphere. They failed almost entirely. Two-dimensional models allowed for some asymmetry and began to produce explosions, but the results were sensitive to the initial conditions. Three-dimensional simulations, which are computationally expensive but far more realistic, are the current frontier. They show that the explosion is inherently turbulent and chaotic. Every simulation is a unique snowflake, shaped by random fluctuations that amplify into large-scale structure. Some stars explode after 200 milliseconds of chaotic churning. Others collapse into black holes after a few seconds. We are beginning to map out this parameter space, but we cannot yet look at a star and tell you whether it will pop or fizzle. We do not know exactly which masses lead to neutron stars, the ultra-dense remnants left behind, and which lead to black holes. The dividing line is fuzzy and depends on factors we still struggle to model, like the exact equation of state of nuclear matter at extreme densities. The explosion itself is a violent laboratory, one that we cannot recreate on Earth. Every time a supernova goes off in our cosmic neighborhood, and we catch its neutrino burst or its gravitational wave signal, we get a fleeting snapshot of the physics at work. But those snapshots are rare. The last supernova visible to the naked eye in our galaxy was in 1604. We are overdue. When the next one comes, it will test everything we think we know. Until then, the inner engine of the most powerful explosions in the universe remains a black box, a place where the laws of physics are stretched to their breaking point and where the outcome is anything but certain. Quasars outshine entire galaxies from the edge of the visible universe. These brilliant beacons are powered by supermassive black holes, millions or billions of times the mass of our Sun, as they swallow surrounding gas and spit out colossal jets of energy. The light from the most distant quasars has traveled for more than 13 billion years, reaching us from a time when the universe was less than 800 million years old. That fact alone presents a staggering puzzle. How did black holes grow so massive so quickly? Standard astrophysics tells us that black holes are born from the collapse of massive stars, seeds that weigh perhaps 10 to 100 solar masses. Even if such a seed began swallowing gas at the maximum possible rate, known as the Eddington limit, where the inward pull of gravity balances the outward push of radiation pressure, it would need something like 1 billion years to reach 1 billion solar masses. But the universe at that early epoch had only a few 100 million years to work with. Something must have sped up the process. One possibility is super-Eddington accretion, where the black hole consumes gas faster than the traditional limit, perhaps through dense, clumpy inflows that do not heat up as much. In these scenarios, the radiation can escape through channels, allowing the black hole to gorge itself without blowing away the fuel. Computer simulations suggest that such rapid feeding could work, but only under very specific conditions. Another idea is the direct collapse of a massive gas cloud. Instead of fragmenting into stars, a giant cloud of primordial hydrogen and helium could collapse directly into a black hole with an initial mass of 10,000 to 100,000 solar masses. That would give the growing monster a huge head start, skipping the need to build up from a stellar seed. The conditions for direct collapse are thought to be rare, requiring a strong ultraviolet background that prevents the cloud from cooling and forming stars, but they might have been more common in the early universe. A third, more exotic possibility is primordial black holes, formed not from stars but from extreme density fluctuations in the first moments after the Big Bang. These hypothetical objects could have been born with a wide range of masses, including the supermassive range, ready-made and waiting to seed the quasars we see. So far, none of these ideas have been confirmed, and each has its own challenges. The James Webb Space Telescope has recently deepened the mystery. Webb is peering back to the very first galaxies and quasars, and it has found supermassive black holes at redshifts beyond 7 that are even more massive than predicted. Some of these objects show signs of rapid growth that strain even the most optimistic accretion models. They appear fully formed, as if they were always there. Webb is revealing that the early universe was a place of violent and efficient assembly, where black holes grew at a furious pace. The observations are forcing theorists to reconsider how quickly matter can be fed to a black hole and whether new physics is required. Each new quasar discovery raises a question. Are we missing a fundamental channel for black hole formation, or is the early cosmos simply more chaotic and gas-rich than we assumed? The monstrous black holes at the centers of distant quasars are not just curiosities. They are signposts pointing to a time when the universe was young, turbulent, and full of hidden processes we have yet to understand. And as Webb continues to scan the sky, it will keep finding these ancient giants, each one a clue to how the darkest objects in the cosmos grew to dominate their galaxies. Neutron stars are already extreme beyond imagination, but there is a class of them that pushes the boundaries of known physics into a new dimension. These are magnetars, the most magnetic objects in the universe. A magnetar is the crushed core of a massive star that went supernova, a ball of nuclear matter no larger than a city, spinning once every few seconds. But its magnetic field is 1 trillion times stronger than Earth's and 1,000 times stronger than that of a typical neutron star. That field is so intense that it can literally warp the shape of atoms, squeezing them into bizarre cigar-shaped structures. The energy stored in that invisible magnetic grip is staggering. Every once in a while, that energy is released in a spectacular eruption called a giant flare. These flares blast out more energy in 1/10 of a second than our Sun produces in 100,000 years. We have only detected a handful of these events, and they come from no more than about 30 known magnetars in our entire galaxy. A closely related phenomenon is the soft gamma repeater, a source that flashes repeatedly with softer gamma rays, sometimes in a storm of hundreds of bursts over a few hours. These outbursts reveal that the magnetic field inside a magnetar is not static. It evolves, twists, and decays over time, and that decay is what powers the flares. But the exact mechanism is not fully understood. How does the magnetic field reconfigure itself? What triggers the sudden release of energy? The leading idea involves a starquake. As the magnetic field shifts, it stresses the solid crust of the neutron star, which is a crystal lattice of nuclei held together by unimaginable pressure. When that stress becomes too great, the crust cracks, releasing a blast of energy. The quake sends seismic waves through the star and rattles the magnetic field, causing a violent reconnection event similar to solar flares but on a scale 1 trillion times more powerful. This magnetar activity has recently become even more mysterious because of its connection to fast radio bursts. In 2020, a magnetar called SGR 1935 plus 2154, located about 30,000 light-years away in the constellation Vulpecula, emitted a pair of extremely bright radio pulses that looked exactly like a fast radio burst but much fainter. For the first time, we caught an FRB equivalent coming from an object inside our own galaxy. That detection confirmed that at least some fast radio bursts come from magnetars. But it also raised new questions. The energy of that local burst was far weaker than the extragalactic FRBs we see from billions of light-years away. Could a single magnetar, under the right conditions, produce a burst 1,000 times more powerful? Or do the most extreme FRBs require a different engine altogether? The link is tantalizing but incomplete. Every burst from SGR 1935 plus 2154 is studied eagerly by teams around the world, hoping to see a pattern that explains both the local and distant events. The magnetic field of a magnetar is so strong that it delves into a regime where quantum electrodynamics, the theory that describes how light and matter interact, begins to break down. In those fields, the vacuum itself becomes birefringent, meaning it bends light differently depending on its polarization. Photons can split into two or even morph into matter-antimatter pairs. The signatures of these quantum effects should be imprinted on the X-rays and gamma rays that the magnetar emits. So far, no telescope has been sensitive enough to see them clearly. But new instruments are on the way. The Imaging X-ray Polarimetry Explorer, or IXP, is already measuring the polarization of X-rays from magnetars. The Chinese Einstein probe is scanning the sky for transient flares. And in the future, the Athena X-ray Observatory will provide even greater detail. Magnetars are natural laboratories for the most extreme physics we can study. They challenge our understanding of matter, magnetism, and quantum fields under conditions that cannot be replicated on Earth. And every time a new flare lights up across the galaxy, we get a glimpse into a world where the rules of reality are bent to their breaking point. The next burst could reveal something entirely unexpected. Galaxies are strung along invisible threads that span the cosmos. When cosmologists run supercomputer simulations of the universe on the largest scales, they see a pattern. Matter is not spread evenly. Instead, it is concentrated into a vast network of filaments, sheets, and nodes with huge empty voids in between. This structure is called the cosmic web. And the filaments themselves are made mostly of dark matter, the invisible stuff that we talked about earlier. But they also contain ordinary gas, hydrogen and helium, heated to millions of degrees by the violence of structure formation. This gas is incredibly diffuse, spread out over millions of light years. It is so thin that it barely emits any light. For decades, it was missing from our census of the universe. We knew it should be there based on the total amount of matter from the Big Bang, but we could not find it. That missing piece is called the missing baryons problem. Baryons are the ordinary particles that make up stars, planets, and people, and a large fraction of them seem to have vanished. The cosmic web filaments turned out to be their hiding place. Recently, astronomers have begun to detect this hidden gas using the Chandra X-ray Observatory and other X-ray telescopes. They look at the light from distant quasars. When that light passes through a filament, certain X-ray wavelengths get absorbed by highly ionized oxygen atoms. That absorption line reveals the presence of the warm-hot intergalactic medium, shortened to WIM. By measuring how strong the absorption is, scientists can estimate how much gas is sitting in those filaments. The numbers are starting to match the missing baryons, confirming that the cosmic web holds the ordinary matter we thought was lost. But the filaments are not simple. They are turbulent and magnetized. The gas is in a delicate balance between heating from shocks and cooling from radiation. The strength and orientation of magnetic fields in these filaments are almost completely unconstrained. Do the fields guide the flow of gas into galaxies? Do they suppress star formation? These questions matter because the cosmic web feeds galaxies. How gas moves along these highways determines how quickly galaxies can build stars and how black holes can grow. The exact thermal and magnetic properties remain a frontier of research, and every new observation of the WIM adds a small piece to a puzzle that stretches across the largest scales we can measure. The cosmic web is the skeleton of the universe, but we are only beginning to trace its veins. Every new quasar absorption line, every new map of X-ray emission, fills in a little more of the picture, revealing how the largest structures connect to the smallest. And hidden within those filaments, the missing baryons tell a story of how the universe organizes itself from the chaos of the Big Bang into the ordered galaxies we see today. Thousands of worlds orbit distant stars, yet we struggle to read their skies. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere, carrying the fingerprints of the gases there. Each gas absorbs specific colors of light, creating a pattern of missing wavelengths, a spectral signature that should reveal what the air is made of. But the same pattern can arise from very different mixtures. This is the degeneracy problem. A thick layer of high clouds can mimic the signature of a different gas. A haze of organic particles can blur the absorption lines until they become almost invisible. Warm water vapor can look like carbon dioxide if the temperature and pressure are just right. So for many exoplanets, we end up with multiple plausible compositions, and we cannot tell which one is correct without additional information. Clouds and hazes are the biggest troublemakers. They scatter light in ways that flatten the spectral features, making the atmosphere appear more uniform than it really is. A planet that is actually rich in methane might look like it has only a bland, featureless envelope if it also has a high-altitude haze. We see this effect clearly in the data from the James Webb Space Telescope. Webb has observed several hot Jupiters, giant worlds that orbit scorchingly close to their stars. The spectra are beautiful and rich, but they often show broad, shallow features instead of the sharp lines we hoped for. For one such planet, called WASP 39b, Webb detected carbon dioxide, water vapor, and even sulfur dioxide, a molecule that forms when starlight drives chemical reactions. That was a triumph, but for many others, the signals are smeared by clouds that we cannot characterize. Super-Earths, rocky planets slightly larger than our own, present an even harder puzzle. Their atmospheres are thinner and the telltale signs are fainter. Webb has begun to study a few of these worlds, such as TRAPPIST-1d and E. The initial results are tantalizing but inconclusive. Some show hints of water vapor, others of carbon dioxide, but the data are noisy and the degeneracies remain. The ultimate goal is to find a true Earth analog, a rocky planet in the habitable zone with an atmosphere that could support life. Biosignatures like oxygen and methane together would be a powerful clue. On Earth, oxygen is produced by photosynthesis, and methane comes from both biological and geological sources. Their coexistence in a single atmosphere, far from chemical equilibrium, is a strong indicator of living processes, but interpreting that signal on a distant world is treacherous. Many non-biological processes can mimic biosignatures. Photochemical reactions can create oxygen without life. Geological outgassing can produce methane. A planet with a thick haze can produce false absorption patterns, and the small size of an Earth-like planet makes its atmospheric signal extremely faint against the glare of its star. We need bigger telescopes, more stable instruments, and years of repeated observations to gather enough light. The challenge is monumental, but the reward would be transformational. Every new spectrum from Webb adds a piece to the puzzle, narrowing the possibilities and ruling out some models. The degeneracy is not infinite. With more wavelengths, better signal-to-noise, and complementary observations from ground-based telescopes, we can gradually break the ambiguity. The search for a second Earth is a marathon, not a sprint, and the atmosphere of each exoplanet is a unique fingerprint waiting for us to learn how to read it. Magnetic fields stretch across entire galaxies, yet their origin remains unknown. Even empty space between galaxies is threaded by invisible lines of force, and these fields are not random. They are coherent, organized, and vast, spanning tens of thousands of light-years. The Milky Way has a large-scale magnetic field that wraps around its spiral arms, and the same is true for many other galaxies. Galaxy clusters, the largest bound structures in the universe, also harbor diffuse magnetic fields that fill the hot gas between their member galaxies. The presence of these fields is not in doubt. We see their effects in the synchrotron radiation emitted by high-energy electrons spiraling along the field lines, and in the way they polarize the light from distant radio sources. But how did these fields come to exist? That is the puzzle. Two main ideas compete. The first is that the fields are primordial, meaning they were generated in the very early universe, perhaps during cosmic inflation or during a phase transition shortly after the Big Bang. In this picture, a weak but pervasive magnetic field was stretched across space as the universe expanded. That seed field later got amplified as galaxies formed and as gas collapsed. The second idea is that the fields were generated much later by dynamo action inside stars and within the turbulent gas of galaxies themselves. A dynamo is a self-sustaining process that converts kinetic energy into magnetic energy. On Earth, the liquid iron core acts like a dynamo, generating our planet's magnetic field. In a galaxy, the rotation and turbulent motions of the interstellar gas can, in principle, do the same thing. But a dynamo needs a seed field to start with, even a tiny one. Without a seed, the dynamo cannot get going. So the question becomes, where did the very first seed magnetic fields come from, even before the first stars formed? That seed could have come from the primordial universe, or it could have been generated by the motion of charged particles in the early plasma, a process known as the Biermann battery. That battery is weak but could have produced fields of the right order to seed later dynamos. The problem is that we cannot easily distinguish between these scenarios by looking at galaxies alone, because the dynamo erases the memory of the initial seed. By the time a galaxy has matured, its magnetic field looks the same regardless of how it started. To find the answer, we have to look at the intergalactic medium, the vast regions between galaxies where the fields are weakest and most pristine. Detecting those fields is extremely difficult. Their strength is probably less than a billionth of a Tesla, 1,000,000 times weaker than Earth's magnetic field. They produce almost no detectable radiation on their own, but there is a clever technique, blazars. Blazars are active galactic nuclei that shoot jets of high-energy particles directly toward Earth. As the gamma rays from those jets travel across the universe, they interact with the faint background light of stars and galaxies, producing pairs of electrons and positrons. Those pairs then interact with intergalactic magnetic fields, causing them to emit secondary gamma rays. By studying the timing and spectrum of the gamma rays we receive, astronomers can infer the strength and structure of the magnetic fields in the intervening voids. The results are still preliminary, but they suggest that intergalactic fields are present at levels consistent with either a primordial origin or a weak battery-seeded dynamo. The uncertainty remains large. Another clue comes from the earliest galaxies seen by the James Webb Space Telescope. If primordial magnetic fields existed, they could have influenced how the first stars and galaxies formed, leaving a subtle imprint on the structure of the early universe. Theorists are now running simulations that include magnetic fields from the start to see if they can reproduce the observed properties of young galaxies. So far, the simulations show that even a tiny primordial field can change the way gas collapses and stars form, but whether that matches what Webb actually sees is still being tested. The deepest mystery is this: we know magnetic fields are everywhere, from planets to galaxies to the voids between them, but we do not know when or how the first lines of force were drawn across the fabric of the cosmos. This is not a minor detail. Magnetic fields affect how gas flows, how stars form, how cosmic rays propagate, and how galaxies evolve. They are a fundamental ingredient of the universe, and we cannot fully understand galaxy formation without understanding their origin. Every new observation of a blazar, every map of polarized radio emission, and every simulation of the early universe is a step toward solving this primordial riddle. The cosmic magnetic field is a ghost that touches everything, and until we know where it came from, a key chapter in the story of the universe remains unwritten. Not every world has a sun to circle. Some planets drift alone through the cold darkness between the stars, never warming themselves in the light of a parent star. For a long time, these rogue planets were purely hypothetical. We assumed that any planet born in a solar system would stay there, bound by gravity. But over the past decade, astronomers have found evidence that a significant number of worlds are cast out into the abyss, and there may be more of these lonely wanderers than there are stars in the galaxy. They are invisible to ordinary telescopes. A planet does not emit its own light. It only reflects starlight, and without a nearby star, it is effectively a black ball against a blacker sky. So how do we find something that gives off no light? The answer is a trick of gravity called gravitational microlensing. When a rogue planet or any massive object passes almost exactly in front of a distant star, its gravity bends the light from that star, acting like a natural lens. The star appears to brighten and then fade in a characteristic curve that reveals the mass of the intervening object. By watching millions of stars for these brief, random alignments, we can catch a rogue planet in the act of crossing our line of sight. The problem is that these events are extremely rare. A single microlensing event might last only a few hours for a planet-sized object, and it requires constant monitoring of a huge patch of sky. Surveys like Auger and MOA have found a few dozen candidate rogue planets, but the numbers are so small that the total population remains a wild guess. Some estimates suggest that rogue planets may be as common as stars, or even more common, with perhaps 100 billion of them roaming the Milky Way alone. That would mean that the majority of planets in our galaxy are not bound to any star at all. How do they get thrown out? The leading formation mechanism is ejection. In the chaotic early years of a planetary system, when giant planets are migrating and jostling for position, gravitational interactions can fling a smaller world into a hyperbolic orbit, sending it careening away from its sun. Computer simulations show that a typical system might eject anywhere from a few to dozens of planets over its lifetime. The giant planets like Jupiter are especially efficient at this. Their powerful gravity can slingshot a planet out of the system completely, like a stone from a catapult. But ejection is not the only way. Theory also allows for rogue planets that form directly from the collapse of a small gas cloud, in the same way that stars form, but on a much smaller scale. These free-floating objects would be born alone, never having belonged to a family. Distinguishing between these two origins is difficult. An ejected planet would be composed of the same material as its parent star, while a directly formed one might have a different chemical composition. But we have no way to sample them yet. The upcoming Nancy Grace Roman Space Telescope, set to launch in the late 2020s, will change this picture dramatically. Roman will carry a powerful wide-field camera and will spend months staring at a dense region of the galactic bulge, taking an image every 15 minutes. It will detect thousands of microlensing events, including many caused by rogue planets. Roman will be able to find objects as small as Mars, perhaps even Mercury, wandering through space. By counting how many such events occur and at what rate, astronomers will finally get a reliable census of the rogue planet population. If Roman finds that these orphans are indeed as common as predicted, it will force us to rethink our entire picture of planetary formation. It would mean that most planets do not stay put, that nature throws away more worlds than it keeps. And it would raise a haunting question: what happens to life on a world that is cast into permanent night, where the only light comes from distant stars that never set? Such a world might still be habitable if it had internal heat from radioactive decay or tidal forces, but its sky would be forever dark. The search for rogue planets is not just a curiosity. It is a window into the violent, chaotic side of planet formation, the side that kicks out most of its children into the void. And when Roman opens its eyes, we may discover that the galaxy is far more crowded with invisible wanderers than we ever imagined. The moon hangs in our sky every night, yet its origin remains a stubborn puzzle. The leading theory tells a dramatic story. A Mars-sized object named Theia slammed into the young Earth about 4.5 billion years ago, blasting a cloud of debris into orbit that eventually coalesced into our satellite. This giant impact hypothesis explains many things, like the moon's small iron core and its lack of volatile elements, but there is a glaring problem. When we compare the rocks brought back by the Apollo missions with samples from Earth's mantle, we find they are almost identical in their isotopic composition. The ratios of oxygen, titanium, and other elements match so closely that they look like they came from the same source. If Theia was a separate world with its own distinct makeup, we would expect a clear chemical difference. The fact that we do not see one is called the isotopic crisis, and it has haunted planetary scientists for decades. Maybe Theia had the same composition as Earth by pure coincidence, but that seems unlikely given the diversity of objects in the early solar system. Perhaps the impact was so violent that the two bodies mixed completely, homogenizing their materials before the moon formed. Computer simulations show that at extremely high energies, a head-on collision can indeed blend the impactor and the target into a single vaporized cloud, erasing any original differences. But those same simulations struggle to create a moon with the right mass and angular momentum. Another possibility is that Theia itself formed in roughly the same region of the solar system as Earth, so its composition was already similar. That would reduce the crisis, but it does not fully resolve it. Newer alternatives have emerged to explain the isotopic match. The multiple impact hypothesis suggests that the Moon was built not from a single giant blow, but from a series of smaller collisions, each adding material from the same source. A more radical idea proposes that the early Earth was not a solid sphere but a cynosure, a huge, donut-shaped cloud of vaporized rock spinning so fast that it had no solid surface. In this picture, a smaller impact could have caused a blob of that spinning cloud to pinch off and form the Moon, using material entirely from Earth. The cynosure model elegantly explains the identical isotopes, but it remains a theoretical construct that has not been directly observed. All of these ideas are being tested with better data. High-precision measurements of lunar samples from the Apollo missions continue to reveal subtle differences, not enough to resolve the crisis but enough to rule out some models. And China's Chang missions have brought back new samples from the far side of the Moon, offering fresh material that is billions of years old. These new rocks carry chemical fingerprints that could tell us whether the Moon truly formed from Earth or from a mixed debris cloud. Upcoming missions like NASA's Artemis program plan to return even more samples, targeting regions that have never been sampled before. Each new rock chip or grain of dust is a witness to the birth of the Moon, and each one holds a clue to how Earth's closest companion came to exist. The isotopic crisis may not be solved today, but the hunt for answers is driving some of the most exciting lunar science in decades. Neutrinos are the ghosts of the particle world, and they carry a secret that could rewrite the laws of physics. These nearly massless particles stream through your body by the trillions every second, passing through the Earth as if it were empty space. For decades, physicists assumed neutrinos had no mass at all. They fit perfectly into the standard model as zero-mass particles. Then in the late 1990s, experiments like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada discovered something astonishing. Neutrinos change flavor as they travel. An electron neutrino born in the Sun can arrive at Earth as a muon neutrino or a tau neutrino. That transformation, called neutrino oscillation, can only happen if neutrinos have mass. It was a Nobel Prize-winning discovery, but it opened a much deeper question. How do neutrinos acquire mass? The standard model provides no mechanism. This forces us to consider new physics beyond the known framework. The leading ideas are the Dirac mass and the Majorana mass. In the Dirac scenario, neutrinos get their mass through the same Higgs mechanism as other particles, but they have a distinct antiparticle, just like electrons do. In the Majorana scenario, the neutrino is its own antiparticle. That may sound like a small distinction, but it has enormous consequences. If neutrinos are Majorana particles, then a rare process called neutrinoless double beta decay becomes possible. In ordinary double beta decay, two neutrons in a nucleus convert into two protons, emitting two electrons and two antineutrinos. If neutrinos are Majorana, the two antineutrinos could annihilate each other inside the nucleus, leaving only two electrons. This process would violate lepton number, the quantum number that counts particles versus antiparticles, and it would point directly to new physics. No experiment has ever seen neutrinoless double beta decay. The current searches, like the Jurda experiment in Italy and the Camland-Zen experiment in Japan, have set strict limits on how often it can occur, pushing the half-life of this decay to more than 10 to the 26th years. That is trillions of times the age of the universe, yet the hunt continues because finding it would prove that the neutrino is its own antiparticle and would give us a concrete number for the absolute mass scale of neutrinos. Beyond the mass mechanism, there are critical parameters of neutrino oscillation that remain unknown. One of the most important is the CP violating phase. CP violation in neutrinos would mean that neutrinos and antineutrinos oscillate at slightly different rates. This asymmetry could be the key to understanding why the universe has more matter than antimatter, a link to the baryogenesis puzzle we discussed earlier. The T2K experiment in Japan and the NRVA experiment in the United States are racing to measure this phase. The early hints suggest that the CP violating angle may be close to its maximum possible value, which would be a tantalizing clue. Another unknown is the mass ordering. We know that neutrinos come in 3 mass states, but we do not know which one is the lightest and which is the heaviest. That ordering affects how neutrinos oscillate as they travel through matter, and it influences the rates of supernova neutrinos and the formation of cosmic structure. Experiments like the Deep Underground Neutrino Experiment, or DUNE, currently under construction in South Dakota, will be sensitive enough to determine the ordering by studying neutrinos sent from Fermilab over a distance of 1,300 kilometers. Deep in the Earth, a huge detector filled with liquid argon will capture the interactions of these particles and reveal their hierarchy. And then there is the role of neutrinos in the most violent events in the cosmos. When a massive star collapses into a supernova, 99% of the gravitational energy is released not as light but as neutrinos. In the span of a few seconds, a supernova emits more neutrinos than the Sun will produce in its entire lifetime. These neutrinos carry direct information from the heart of the explosion, from the core where densities and temperatures are so extreme that no other messenger can escape. The burst of neutrinos from supernova 1987 in the Large Magellanic Cloud, detected by 3 experiments around the world, confirmed the basic picture of core collapse. But we only saw about 24 neutrinos. The next galactic supernova will give us a flood of them, potentially tens of thousands of events in detectors like Super Kamiokande, IceCube, and DUNE. That data will allow us to peer inside the collapsing core in real time, measuring the mass and flavor composition of the neutrino flux. It will test our models of supernova physics with unprecedented precision. And because neutrinos travel at nearly the speed of light without being scattered, they will arrive hours before the light from the explosion, giving astronomers an early warning to turn their telescopes toward the dying star. Neutrinos are the smallest messengers of the largest forces. They connect the quantum world of particle physics to the cosmic scale of stellar death. Every unknown parameter, every unseen decay, every future burst from a nearby supernova is an opportunity to reach beyond the standard model. The ghost particles hold the key to whether our understanding of mass, matter, and the universe is complete or just the beginning. The cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos when it was just 380,000 years old. It is almost perfectly smooth, with temperature variations of only a few parts in 100,000. But in that nearly perfect uniformity, there is a blemish, a large, strangely cold patch that should not exist. Astronomers call it the CMB cold spot, a region of the sky where the temperature is significantly lower than average, and it spans an area equivalent to about 20 full moons across. Its size and depth make it one of the most statistically improbable features in the entire map. The standard model of cosmology, which explains the rest of the CMB so beautifully, predicts that such a large and deep cold spot should occur by random chance only about once in every 1,000 universes. That is not quite impossible, but it is deeply suspicious. Something must either be wrong with our understanding of how these fluctuations are generated, or there is a real physical cause lurking beyond the standard picture. The leading explanation involves a supervoid. A supervoid is a vast, nearly empty region of space, hundreds of millions of light years across, where the density of galaxies and matter is much lower than average. As a photon from the cosmic microwave background travels through such a void, it experiences a subtle effect called the late-time integrated Sachs-Wolf effect. The void has less gravitational pull than the surrounding universe, so as the photon climbs out of the void, it loses a tiny bit of energy and appears cooler when it reaches us. This effect is real and has been measured for smaller voids, but to account for the full size and depth of the cold spot, the supervoid would have to be enormous and exceptionally underdense. In recent years, surveys of galaxies in that direction have indeed found a large underdensity, a region that contains far fewer galaxies than expected. But the match is not perfect. The measured underdensity is not quite large enough to explain the full temperature drop. Either the void is even emptier than the galaxy counts suggest, or there is another effect at play. A more exotic possibility is that the cold spot is a sign of non-Gaussian primordial fluctuations. In the simplest models of cosmic inflation, the initial quantum fluctuations that seeded all structure follow a Gaussian distribution, meaning they are randomly and symmetrically distributed. But if inflation involved more complex fields or interactions, the fluctuations could have a non-Gaussian tail, producing rare, large amplitude features like this cold spot. That would be a direct window into the physics of inflation, a clue that the simple picture is not the whole story. And then there is the most troubling possibility: the cold spot might not be cosmic at all. It might be a systematic artifact from our own local environment or from the instruments. One clue is that the cold spot aligns very closely with the ecliptic plane, the plane of Earth's orbit around the Sun. That alignment is suspicious because it suggests a possible link to foreground emission from our own solar system, maybe from dust or from the Sun's magnetic field interacting with the intergalactic medium. The Planck satellite, which mapped the CMB with unprecedented precision, took great care to subtract all known foregrounds, but a subtle residual could still mimic a cold spot. Statistically, the alignment with the ecliptic is a red flag that has not been fully explained, so the cold spot remains a puzzle on multiple levels. If it is a real primordial feature, it challenges the Gaussian assumption of inflation. If it is a supervoid, it requires a larger underdensity than we have seen. If it is a systematic, it teaches us that our maps still hold hidden imperfections we must understand. Each new observation of the galaxies in that direction, each improved model of foreground subtraction, narrows the possibilities. The cold spot is a crack in the smooth facade of the cosmic microwave background, and through that crack we might glimpse either a new kind of physics or a reminder that even our best maps are still works in progress. The answer lies in the details, and the details are still being gathered. The same cold spot points to a much larger emptiness that surrounds our own galaxy. In the cosmic web of matter, where filaments of galaxies weave together, there are also vast regions that are almost empty. These are voids, and one of them sits right next door to us. Astronomers call it the local void, and it is a cavernous stretch of space that lies just beyond the edge of the Milky Way and its neighbors, the local group. The local void is not completely devoid of anything, but its density is far lower than the cosmic average. It is a desert compared to the crowded cities of galaxies we see elsewhere. Its presence has been known for decades, but we still cannot say exactly how large it is, what shape it takes, or how much matter hides within its dim interior. The reason is simple. The local void is largely blocked from view by the disk of our own galaxy, the same dusty veil that hides the Great Attractor, so we cannot simply point a telescope at it and take a picture. Instead, astronomers map the positions and velocities of nearby galaxies, building a three-dimensional picture of the region. What they see is a bubble of emptiness that stretches across roughly 150 million light-years, maybe more, maybe less. Galaxies that lie on the edge of this void are moving away from it, as if falling into the denser surrounding regions, and our own local group is one of those fleeing galaxies. Our peculiar velocity, that 2 million km/h drift we talked about earlier, is partly caused by the gravitational tug of the Great Attractor, but also by the push from this local emptiness. Voids like this are not just empty space, they are laboratories for testing the very nature of gravity. In standard cosmology, gravity pulls matter together, and voids form as a natural consequence of expansion and gravitational collapse. But if modified gravity theories like MOND are correct, gravity might behave differently in low-density environments. In a void where the gravitational acceleration is tiny, MOND would predict a different rate of growth for structure. Galaxies on the edges of voids might show different rotation curves or peculiar motions than expected under dark matter models. So far, the observations are not precise enough to distinguish between the two, but the local void is one of the best places to look because it is nearby and relatively free of other complicated structures. Voids also affect how galaxies form and evolve. Galaxies that live inside voids are generally smaller, fainter, and more isolated than those in dense clusters. They have less gas and form stars more slowly. The Milky Way sits on the outskirts of the local void, and some researchers wonder whether our galaxy's own quiet history was shaped by this proximity. Did the void starve our galaxy of fresh gas, slowing down star formation and leaving us in a relatively calm state? The question is open. The exact boundaries of the local void are uncertain because we only see a few galaxies on its far side. Future surveys using the James Webb Space Telescope or the Nancy Grace Roman Space Telescope will peer through the galactic plane in infrared light, revealing more of the hidden landscape. When that happens, we will finally map the void that surrounds us. For now, we live on the edge of an emptiness, a bubble in the cosmic foam, and that emptiness may hold clues to the most basic laws of physics. The local void is not just a hole, it is a window. The most powerful explosions in the universe announce themselves in a flash of gamma rays that outshines every star in the host galaxy. Gamma-ray bursts, or GRB, are brief but brilliant events that release more energy in seconds than the Sun will emit in its entire lifetime. Astronomers have long divided them into two families based on duration. A long GRB lasts more than 2 seconds, sometimes stretching for minutes. A short GRB lasts less than 2 seconds, often just a fraction of a second. And that simple time cutoff is the key to unlocking their very different origins. Long gamma-ray bursts come from the collapse of massive stars, stars that have burned through their fuel and can no longer support their own weight. The core crumbles into a black hole, and a powerful jet of material, funneled by intense magnetic fields, drills its way through the dying star. As that jet breaks free into space, it produces a brilliant flash of gamma rays. These bursts are almost always found in galaxies that are actively forming new stars, exactly where massive, short-lived stars are born and die. Short gamma-ray bursts tell a different story. They originate from the violent merger of two neutron stars, or a neutron star and a black hole. As these ultra-dense objects spiral together, they send out ripples in space-time, gravitational waves, and at the moment of merger, a narrow jet of material is launched. That jet is what produces the short gamma-ray burst. The host galaxies of short bursts are often old and quiet, places where massive stars have long since vanished, but where the compact remnants of past stellar lives still orbit each other. In 2017, a breakthrough observation linked a short gamma-ray burst, GRB 170,817A, with a gravitational wave signal from a neutron-star merger, confirming the connection beyond doubt. The same event also produced a kilonova, a faint, rapidly fading glow powered by the radioactive decay of heavy elements forged in the merger. This kilonova provided direct evidence that neutron-star mergers are the cosmic forges for gold, platinum, and other elements heavier than iron. That single observation tied together gravitational waves, gamma rays, and heavy element synthesis in one spectacular event. But even with this success, the details of how GRBs work remain unresolved. The jet must punch through the surrounding material, and the process by which the jet converts its energy into gamma rays, the prompt emission, is still a subject of intense debate. Some models propose that the gamma rays come from internal shocks within the jet, where faster material catches up and collides with slower material. Others suggest that magnetic reconnection, similar to solar flares but on a vastly larger scale, is the driving mechanism. The role of magnetic fields is especially mysterious. In long GRBs, the collapsing star's magnetic field is thought to be amplified by the violent infall, creating a funnel that focuses the jet. But the field's strength and geometry are difficult to measure directly, and simulations struggle to capture the full complexity. In short GRBs, the magnetic field of the merging neutron stars is even more extreme, and it may determine how the jet is launched and how long it lasts. Observations show that some GRBs do not fit neatly into the 2-second cutoff. There are long bursts that show no evidence of a supernova, suggesting they might come from mergers after all, and short bursts that are followed by a slowly fading afterglow that resembles a kilonova but with unusual properties. These outliers challenge the tidy classification scheme. Nature does not always read our textbooks. Some long bursts might be from a different kind of collapse, perhaps involving a magnetar rather than a black hole. Some short bursts might come from a neutron star black hole merger that produces a longer-lived jet. Each new detection from the Swift Observatory, the Fermi Gamma-Ray Space Telescope, and the ground-based follow-up telescopes adds a data point that tests our models. The imager on the upcoming SVOM mission, a collaboration between China and France, will detect GRBs and quickly relay their positions to telescopes around the world, catching the prompt emission and the early afterglow like never before. Gamma-ray bursts are not just cosmic fireworks, they are probes of the most extreme environments in the universe, places where gravity, magnetism, and nuclear physics combine in ways we have not yet fully grasped. Every burst carries a message from a dying star or a merging pair of dead stars, a message written in the language of high-energy photons. We are still learning how to read it. Black holes come in two familiar sizes, but a third kind should exist between them. Stellar mass black holes form from collapsing stars and weigh in at a few to 100 times the mass of our Sun. Supermassive black holes, the ones at the centers of galaxies, are millions or billions of times heavier. But what about the ones in the middle? For decades, astronomers have searched for intermediate mass black holes, objects weighing 1,000 to 100,000 solar masses, and they remain frustratingly elusive. That gap in the mass spectrum is more than a curiosity. It is a missing link that could tell us how supermassive black holes got so huge in the first place. If we could find a steady population of these mid-sized giants, we could trace the path from stellar corpse to galactic center, but the problem is they are incredibly hard to spot. A supermassive black hole announces itself by the blazing glow of gas it feeds on, visible across billions of light years. A stellar mass black hole reveals itself through the motion of a companion star or by the bright burst of a merger. An intermediate mass black hole, however, exerts only a faint gravitational influence on its surroundings. It does not have enough pull to create a brilliant accretion disk, yet it is too massive to be easily found in the tidal streams of a star cluster. The few strong candidates we have come from unusual places. One is in the globular cluster Omega Centauri, a dense ball of millions of stars orbiting our Milky Way. Astronomers measured the speeds of stars near the cluster's center and found that something heavy, roughly 40,000 solar masses, is tugging them. Another candidate sits in a dwarf galaxy called M54, and a third was seen in the center of a small galaxy far away. But in every case, the evidence is indirect and the uncertainties are large. It is possible that these signals come from a cluster of smaller black holes or from a dense collection of neutron stars rather than a single massive object. To confirm an intermediate mass black hole, we need to see its gravitational influence at a scale where the signal cannot be confused with anything else. The leading ideas for how these objects form fall into two camps. The first is runaway mergers. In a dense star cluster, the cores of large stars sink toward the center, and over time, collisions between stellar mass black holes could pile up, building a black hole of a few thousand solar masses. But that process needs a cluster that stays dense for a long time, and our simulations still struggle to reproduce the exact conditions. The second idea is direct collapse. In the early universe, some clouds of gas might have been so massive and poor in heavy elements that they collapsed directly into a black hole without forming stars first. These seeds could have been born with 10,000 solar masses, skipping the need for any merger chain. Both pathways remain hypothetical. The next generation of gravitational wave detectors will change the search completely. The Laser Interferometer Space Antenna, or LISA, is a constellation of 3 spacecraft planned for launch in the 2030s. It will detect gravitational waves in a frequency range that stellar mass mergers do not reach. When 2 intermediate mass black holes spiral together and merge, they produce a signal that LISA can pick up from billions of light-years away. Unlike the ground-based observatories, which see only the final moments of a merger, LISA will catch the slow, years-long dance of the inspiral, tracking the orbit with exquisite precision. Each such event will give us not just the mass of the merged object, but also the masses of the 2 partners and the distance to the source. A catalogue of just a few tens of these mergers will tell us how many intermediate mass black holes exist and how they are distributed across the cosmos. LISA will also see the signal of a stellar mass black hole falling into a supermassive black hole, a process called extreme mass ratio inspiral, which will further map the population. But the intermediate mass realm is its prime target. If LISA finds a strong population, it will confirm the runaway merger scenario or the direct collapse scenario depending on the masses and rates. If it finds almost none, it will mean that these black holes are rare and that supermassive black holes must have grown through a different channel, perhaps by swallowing gas continuously rather than through mergers. The missing link is out there, hiding in the spaces between the black holes we know. When LISA finally opens its ears to the universe, it will hear a chorus of whispers from these hidden giants. And that sound will tell us whether the middle of the black hole family tree is full or empty, answering a question that has haunted astrophysics for a generation. The cosmic microwave background holds another unsettling pattern hidden in its faintest variations. When scientists map the oldest light on the very largest scales, they find that the most prominent features, the ones corresponding to the widest angles across the sky, are not randomly oriented. They line up with something on Earth, specifically the plane of our own orbit around the Sun, the ecliptic, and also with the equinox, the direction where the Sun crosses the celestial equator each spring. This alignment should not exist. The cosmological principle, one of the bedrock assumptions of modern cosmology, states that the universe is isotropic, meaning it looks the same in every direction. There is no special axis, no privileged vantage point, yet here, in the most ancient light we can see, there is a hint of a preferred direction. Astronomers have given this anomaly a dramatic name, the axis of evil. The pattern appears in what are called the low multipole moments of the CMB. These are the broadest, largest scale features in the temperature map, the ones that stretch across the entire sky. In a perfectly isotropic universe, these large-scale features would be randomly oriented, with no correlation to any external coordinate system. Instead, the quadrupole and octupole, the second and third largest modes, appear to be aligned with each other and with the ecliptic and equinox. The probability of such an alignment happening by pure chance is low, though not vanishingly small. Some researchers argue it is just a statistical fluke, a rare but expected fluctuation in a universe of infinite possibilities. Others suspect it is a subtle foreground contamination from our own solar system or the Milky Way, a leftover signal that was not fully removed during the data processing. The Planck satellite, which mapped the CMB with extraordinary precision and multiple frequency bands, confirmed the anomaly. The alignment persists even after the most careful subtraction of dust, gas, and galactic emission. That makes it harder to dismiss as a mundane artifact. The cause remains unknown, and that uncertainty opens a door to more radical explanations. Maybe the universe does have a preferred direction, a subtle violation of the cosmological principle that would force us to rethink the standard model of cosmology. Some theories of anisotropic inflation propose that the early universe expanded faster along one axis than the others, leaving a permanent imprint in the CMB. Other ideas invoke a large-scale magnetic field from the early universe, or even the influence of a parallel universe pulling on our own. These ideas are speculative, but the fact that the anomaly persists across multiple independent datasets means it cannot be ignored. The axis of evil is a quiet whisper that the smooth, uniform picture of the cosmos might have a hidden crack, and if that crack is real, it would mean that the universe on its largest scales is not as democratic as we thought. Some directions are special. Why they align with the geometry of our own planetary system is a mystery that deepens the puzzle. It could be a coincidence, a mistake in our maps, or the first sign of a new layer of reality waiting to be uncovered. What if the early universe left behind actual scars in spacetime? As the cosmos cooled and expanded, it went through a series of phase transitions, much like water freezing into ice. When water freezes, defects can form in the crystal lattice, tiny cracks or boundaries where the structure is imperfect. In the same way, cosmologists propose that as the universe underwent its own phase transitions, topological defects could have been frozen into the fabric of reality. One of the most intriguing types is a cosmic string, a one-dimensional thread of pure energy, thinner than a proton but stretching for millions of light years across the cosmos. These strings would be incredibly dense, a single centimeter of cosmic string containing as much mass as a mountain. And because they are so massive, they would warp the space around them, acting like gravitational lenses that bend the light from anything behind them. If a cosmic string passed between us and a distant galaxy, we would see that galaxy split into two identical images, a telltale signature that has been searched for but never convincingly found. Cosmic strings would also leave a distinct imprint on the cosmic microwave background, creating a thin, sharp line of temperature variation as the string moved across the sky. No such line has been seen in the Planck data, but the search continues because the signal could be subtle or the strings could be extremely rare. If they do exist, cosmic strings could have acted as seeds for the formation of galaxies and clusters, offering an alternative to the standard picture where quantum fluctuations from inflation do all the work. The idea is a dark horse in cosmology, one that refuses to die because it is so deeply rooted in fundamental physics. To test the idea, astronomers have turned to the most precise clocks in the universe, pulsars. These rapidly spinning neutron stars beam out radio pulses with the regularity of a lighthouse. If a cosmic string were to pass between Earth and a pulsar, the distortion of spacetime would cause a tiny, predictable shift in the arrival time of the pulses. By monitoring an array of pulsars across the galaxy, the North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, and similar projects have been searching for those shifts. So far, they have seen nothing definitive, but the limits they have placed are already ruling out the most optimistic models of cosmic string density. If strings are out there, they must be extremely light or extremely scarce, yet the possibility remains open and the hunt continues with ever more sensitive timing arrays. If a cosmic string were ever detected, it would be a direct window into the physics of the early universe, a fossil from a time when the fundamental forces were just separating. Until then, they remain one of the most elegant and elusive predictions of particle physics and cosmology, a ghost that might be hiding in the spaces between the stars. Every atom in your body was forged in some distant cosmic event. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of it came from stars that lived and died long before our sun was born. But the story of how each element was created is far from settled. We know that most of the lighter elements up to iron are built up inside stars through nuclear fusion, a slow process that releases energy. Heavier elements, however, require a different kind of alchemy. The slow neutron capture process, or S process, happens in stars that have reached the asymptotic giant branch stage. These are aging, swollen stars where helium is being burned in a shell around a carbon-oxygen core. Neutrons are released in small numbers, and they are captured by atomic nuclei at a leisurely pace, building up elements like strontium, barium, and lead over thousands of years. This S process is well understood, and it explains about half of the heavy elements we see, but the other half, the elements like gold, platinum, and uranium, come from a much more violent pathway, the rapid neutron capture process, or R process. In the R process, neutrons are slammed into nuclei so quickly that there is no time for radioactive decay between captures. This creates super heavy, unstable nuclei that then decay into stable heavy elements. The R process requires an environment flooded with neutrons, and for decades the leading candidate was a supernova explosion. But recent observations have pointed strongly to a different source, the merger of two neutron stars. When these ultra-dense dead stars spiral together and collide, they eject a cloud of neutron-rich material that races through the R process, forging vast amounts of heavy elements. The event in 2017 that produced gravitational waves and a gamma-ray burst also produced a kilonova, a faint, rapidly fading glow powered by the radioactive decay of these freshly made elements. The spectrum of that kilonova showed clear signatures of gold and platinum, confirming that neutron star mergers are indeed a major source, yet the question of relative contribution remains open. How much of the universe's gold comes from mergers and how much from rare supernova? The simulations are not yet precise enough to give a clear answer. One reason is the difficulty in modeling the full R process. The nuclear physics involves thousands of exotic isotopes that have never been studied in a laboratory. Their properties, such as half-lives and neutron capture rates, must be extrapolated from theoretical models, introducing large uncertainties. The environment itself, the expanding, turbulent cloud of neutron-rich material, is also extremely challenging to simulate. We need more observations of kilonovae, more events like the 2017 merger to calibrate our models. Each new kilonova provides a unique fingerprint of the elements produced, allowing us to reverse engineer the conditions. But such events are rare, perhaps only a handful per million years in a galaxy like ours. That makes the hunt for them a long-term effort. And then there is the P process, which produces a handful of rare, proton-rich isotopes like those of molybdenum and ruthenium. These isotopes cannot be made by neutron capture because they already have too many protons. Their origin is perhaps the most mysterious of all. Some may come from supernova, but the yields never quite match observations. Others might be produced in neutrino-driven winds from neutron stars or in the collapse of a massive star to a black hole. No single site has been convincingly identified. The periodic table is our map of the elements, but the cosmic story behind each square is incomplete. We know the major chapters, the S process in giant stars, the R process in neutron star mergers, but the details and the missing pages, the exact fractions, the role of supernova, the P process orphan isotopes all remain unwritten. Every new observation of a kilonova, every improved measurement of nuclear properties, fills in a small piece of the puzzle. The stardust that makes us who we are has a complicated genealogy, and we are still tracing its roots. The same elements that built our bodies are scattered across countless worlds. With billions of planets in our galaxy alone, the odds that life has arisen elsewhere seem staggeringly high. Yet when we scan the skies, we hear nothing. No signals, no artifacts, no evidence of any civilization beyond our own. This silence is the heart of the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The contradiction is simple and profound. The numbers suggest extraterrestrial life should be common, but our observations show a universe that appears empty of anyone else. Over the decades, many possible answers have been proposed, and each one carries deep implications for our own future. One possibility is that life itself is extremely rare, that the jump from non-living chemistry to a living cell is a cosmic fluke that happens only once in a galaxy or once in the entire universe. This is called the rare Earth hypothesis, and it suggests that the conditions that gave rise to us, a stable star, a large moon, a protective magnetic field, plate tectonics, and the right mix of elements, are so unusual that we are effectively alone. Another idea is that the great filter lies ahead of us, not behind. Perhaps civilizations arise frequently, but they inevitably destroy themselves before they can spread across the stars through war, environmental collapse, or technological runaway. This would mean that the silence is a warning, a sign that intelligent life tends to self-destruct once it reaches a certain level of complexity. A third possibility is that we are not being heard because we are not listening in the right way. Civilizations might communicate using methods we have not yet imagined, or they might choose to remain hidden, perhaps for their own protection. The zoo hypothesis suggests that advanced beings are deliberately avoiding us, treating our solar system as a protected preserve, waiting for us to reach a certain stage of development before making contact. The fraction of civilizations that become detectable may be vanishingly small. Many could be out there, but they may not emit signals we can recognize. They might use directed energy beams instead of broadcast radio, or they might have moved their existence entirely into virtual realms, leaving the physical universe silent. In recent years, the search for technosignatures has expanded far beyond radio waves. Astronomers are now looking for industrial pollution in exoplanet atmospheres, for artificial light from the night side of distant worlds, for megastructures that block starlight, and for the waste heat of massive energy consumption. The James Webb Space Telescope has begun to study the atmospheres of nearby rocky planets, and while it has not found any obvious signs of technology, the search is just beginning. The Future Habitable Worlds Observatory, planned for the 2040s, will be a direct imaging telescope designed to take spectra of Earth like planets around Sun-like stars. It will be sensitive enough to detect biosignatures like oxygen and methane, and potentially even technosignatures like chlorofluorocarbons, the same chemicals that once damaged our own ozone layer. If a civilization out there is anything like ours, those chemicals would be a dead giveaway. The Fermi paradox is not a puzzle that will be solved by a single discovery. It is a framework that forces us to confront our own place in the cosmos. Every new exoplanet found, every new search for signals, every null result refines the probabilities. The silence could be a sign that we are rare, or that we are doomed, or that we are simply not ready. But the search itself is a declaration that we are willing to listen, and that willingness might one day be answered. Until then, the stars keep their secrets, and the great silence remains the most profound mystery of all. The farthest light we will ever see marks a boundary we cannot cross. That boundary is not a wall, not a physical edge, but a horizon in time. Light travels at a finite speed, roughly 300,000 kilometers per second, and the universe itself has only existed for about 13.8 billion years. So the most distant light that can possibly reach us was emitted from a point in space that was, at that moment, close enough for its rays to have traveled all the way here over the lifetime of the cosmos. That region, a sphere with a radius of about 46.5 billion light-years, is our observable universe. Everything inside it we can see. Everything beyond we cannot, not yet and never, because the expansion of space is carrying those distant regions away from us faster than light can ever catch up. This horizon is called the particle horizon, and it marks the absolute limit of our vision. Beyond it, galaxies may be forming, planets may be orbiting stars, civilizations may be rising and falling, but their light will never reach our telescopes. The universe beyond the horizon is not a theoretical abstraction. It is as real as the stars we see tonight, but we have no direct evidence of what it contains. The simplest assumption, based on the cosmological principle, is that it looks much like our own patch, filled with billions of galaxies laid out across a vast cosmic web. But there are deeper possibilities that challenge that picture. One is that the universe is finite but has a strange topology, like a three-dimensional surface that curves back on itself. If the universe were closed like the surface of a sphere, then traveling in a straight line long enough would eventually bring you back to your starting point. Such a universe would have no boundary, but it would have a finite volume, and a closed universe would leave a subtle imprint on the cosmic microwave background. The geometry of space affects how the oldest light travels. If the universe were closed, the largest temperature fluctuations we see in the CMB would appear slightly larger than in a flat universe, and the angular size of those fluctuations would be different. Current data from the Planck satellite strongly favors a flat universe, but the uncertainties are still large enough that a small curvature cannot be ruled out entirely. A more radical possibility is that our observable universe is just one bubble among many in a vast multiverse. In this picture, the period of cosmic inflation that stretched our tiny patch into the cosmos we see today may never have stopped. It could be ongoing in other regions, constantly spawning new bubble universes, each with its own physical constants, its own laws of physics, perhaps even different numbers of dimensions. We would never be able to confirm or disprove the existence of those other bubbles because no signal from them can ever reach us. The multiverse is a logical consequence of some inflationary models, but it remains a philosophical idea, not a testable theory. Yet there are ways to push the boundary of our knowledge without crossing the horizon. One is to look for patterns in the cosmic microwave background that could only arise if the universe had a prior phase, a bounce instead of a Big Bang singularity, or if a bubble universe collided with our own during inflation. Such collisions would leave a circular pattern in the CMB, a bruise on the oldest light. The Planck satellite searched for these circles and found nothing convincing. But future missions with higher sensitivity, like the upcoming LIGO satellite and the ground-based Simons Observatory, will scan the CMB with even greater precision, looking for any hint of a signal from beyond our cosmic horizon. The Hubble volume is not just a limit, it is a question mark. Everything we know, every galaxy we have ever photographed, every particle we have ever detected, exists within that sphere. Beyond it lies a realm we can only guess at, a realm that may be infinite or finite or made of countless other universes, and the deepest mystery is that we may never know. The horizon defines the range of our knowledge, but it also reminds us that the universe is larger than our ability to see. Every map we draw has an edge, and that edge is where the next great questions lie. Time itself may be the most stubborn mystery of all. We experience it as a one-way street. Eggs break but never unbreak. Tea cools but never heats up on its own. Memories accumulate and we age. This relentless march from past to future is called the arrow of time, and at its heart lies a simple physical law: entropy always increases. Entropy is a measure of disorder, and in every closed system, disorder grows. The universe as a whole is no exception. But here is the puzzle that ties together the smallest and largest scales of physics. If entropy always increases, then the universe must have started in a state of incredibly low entropy, a state of almost perfect order. Why? The Big Bang did not begin with a chaotic, featureless soup. It began with a smooth, uniform, and extraordinarily compact patch of spacetime. That smoothness is a condition of low entropy. If the early universe had been slightly more lumpy or slightly less uniform, entropy would have been higher, and we would not be here to ask the question. The universe seems to have been fine-tuned for order. The thermodynamic arrow of time, the one that governs teacups and eggs, points in the same direction as the cosmological arrow, the expansion of the universe. When the cosmos expands, entropy can increase because there is more space for disorder to spread. But if the universe were to stop expanding and begin to contract, would time reverse? Some theorists have speculated that a collapsing universe would see entropy decrease and the arrow of time would flip. Yet that remains pure speculation because we have no evidence that expansion will ever halt. The link between the two arrows is a deep clue. It suggests that the origin of time's direction is written into the initial conditions of the Big Bang itself. But why were those conditions so special? Why was the early universe so low in entropy? One possible answer comes from quantum gravity, the yet incomplete theory that merges general relativity with quantum mechanics. In some quantum gravity models, time is not a fundamental property but an emergent one, arising from the statistical behavior of more basic entities. In such a picture, the Big Bang might not have been a true beginning. It could have been a bounce from a previous contracting phase where entropy was reset to a low value by the extreme gravitational conditions. Or in the multiverse scenario, different bubble universes might start with different initial entropies, and by anthropic selection we happen to live in one that is low enough to allow complexity. But these are ideas, not answers. The arrow of time remains the most intimate and the most cosmic of mysteries. It governs every moment of our lives, yet its ultimate origin is tied to the birth of the universe and the nature of spacetime itself. The same fundamental physics that creates black holes and drives the expansion of the cosmos may also be the reason we cannot remember tomorrow. From the invisible scaffolding of dark matter to the silent horizons beyond our vision, every thread of this journey leads back to the same truth: the universe is not finished revealing itself. Time, the one thing we all take for granted, may be the last secret it chooses to share. From the invisible scaffolding of dark matter to the horizon of time itself, each mystery we have explored is an open door. We have wandered through 30 puzzles, from the ghostly pull of unseen mass to the silent emptiness beyond our cosmic horizon. Every one of them is a reminder that our understanding is still young, still growing, still reaching for answers that may transform everything we think we know. The universe does not hand out its secrets easily. It hides them in the faint ripples of ancient light, in the unexpected behavior of distant galaxies, in the subtle signals of particles that barely interact with the world. But that is the thrill of the chase. Each unanswered question is not a failure. It is an invitation to look deeper, to ask better questions, and to push the boundaries of what we can imagine. The scientists who build the telescopes underground, who run the simulations that span years of supercomputer time, who stare at the same patch of sky night after night hoping for a single flash, they are driven by the same curiosity that makes us look up at the stars. And that curiosity is not a luxury, it is part of being human. The vastness of the cosmos can feel humbling, even overwhelming, but it is also a source of endless wonder. Every discovery we make, every mystery we solve, opens up new mysteries we could not have foreseen. That is the nature of exploration. The more we learn, the more we realize how much remains to be known. And that is not a discouraging thought, it is an exciting one. There will always be more to discover, more to understand, more to share. So as this journey through 30 cosmic puzzles comes to a close, remember that the search does not end here. The next great mystery is waiting. It might be revealed by a new telescope, a deeper simulation, or a sudden flash of insight from a mind that refuses to accept the easy answer. And you can be part of that story just by staying curious, by asking questions, and by sharing what you learn. If you enjoyed this exploration, consider subscribing to join us on the next one. Hit the like button if you believe the universe still has secrets worth uncovering, and share this video with someone who loves to wonder, because the greatest discoveries are not made alone. They are made together by a community of people who never stop looking up. Thank you for spending this time among the mysteries of the cosmos. Keep your eyes on the sky and your mind open to the unknown.